Bismillahirrahmanirrahim. Assalamu alaikum, dear student. My name is Dr. Muhammad Adnan Asgar, and we are discussing about the synthesis and design of inorganic materials under the subject of advanced inorganic material chemistry. We have studied about the gas phase methods, in which we are discussing the vapor phase transport method in the last lecture. In this method, we have learned some of the renowned examples, including the platinum, chromium, and nickel elements, along with the tungsten, and the copper oxide. Now we are going to discuss some of the other aspect of the method, include vapor phase transport method in actually the gas phase methods. There are many examples of using this method to prepare binary, secondary, tertiary, and even quaternary compounds. Some examples of vapor phase transport methods of chemical synthesis are as under. Number 1A is preparation of calcium Ca2SNO4, calcium oxide, and tin oxide. It actually, calcium oxide and tin oxide actually react slowly. According to this equation, we can see that calcium oxide and tin oxide react together and change into calcium tin oxide, which is Ca2SNO4. In the presence of gaseous carbon monoxide, tin oxide converts to gaseous tin oxide, which is chemically transported. SNO2, which is in solid state, is reacted with carbon monoxide and change into SNO and carbon dioxide, which is actually subsequently reacts with calcium oxide and carbon dioxide to give calcium tin oxide and carbon monoxide. The B process is of chemical vapor phase transport methods is actually the preparation of nickel chromite. Nickel chromite is NiCr2O4. Nickel chromite is synthesized by the reaction of nickel oxide by the reaction of chromium oxide in the presence of oxygen, and then with reaction of chromium oxide with nickel oxide. These reactions of nickel oxide and chromium oxide speed up in the presence of oxygen, since gaseous chromium oxide CrO3 forms, which migrates to the nickel oxide. In this equation, we can see that chromium oxide Cr2O3, which is actually solid in nature, is reacted with the oxygen and change into chromium oxide CrO3, which is a gaseous molecule. The CrO3 is reacted with nickel oxide, which is solid molecule, and then it subsequently change into nickel chromite and with oxygen. Nickel chromite means NiCr2O4. The C is preparation of niobium silicide, which is NB5Si3. For the synthesis of niobium silicide, metallic niobium and silicon Si2O2 do not react under vacuum. For example, at about 1100 degrees Celsius, but in the presence of hydrogen, gaseous silicon oxide forms, which migrates to niobium Nb. Silicon dioxide, which is actually a solid molecule, is reacted with the hydrogen gas and change into silicon oxide and water. And then this silicon oxide SiO is reacted with niobium and change into niobium silicide Nb5Si3 and niobium oxide NbO. Alternatively, in the presence of iodine, gaseous niobium iodide is formed and is subsequently transported to the silicon dioxide. Niobium, which is solid molecule, is reacted with iodine and then changed into niobium iodide, and this niobium iodide NbI4 is further reacted with the silica, which is solid molecule, and then change into niobium silicide Nb5Si3 and iodine and niobium oxide. In D part, the synthesis or preparation of aluminium sulphide. For the synthesis of aluminium sulphide Al2S3, aluminium and sulfur react slowly at 800 degrees Celsius. Since liquid aluminium becomes coated with a skin of aluminium sulphide, which acts as a diffusion barrier to further reaction. In the presence of iodine, however, and with a temperature gradient of 100 degrees Celsius, aluminium sulphide separates a large colorless crystals at cool 700 degrees Celsius, and the product aluminium sulphide Al2S3 is effectively transported via formation of gaseous aluminium iodide. Aluminium and sulfur element are reacted and change into Al2S3, and this Al2S3 is then further reacted with iodine and change into aluminium iodide and sulfur gas. E is the preparation of Cu3TaSe4, copper, titanium and selenide. Copper, Cu, Ta and Se are actually heated at about 800 degrees Celsius in the presence of iodine. Transport occurs to give Cu3TaSeO4 at 750 degrees Celsius, presumably by means of gaseous complex iodide intermediate. Preparation of zinc tungstate ZnWO4. For the synthesis of Z tungsten, zinc oxide and tungsten oxide are heated at 1060 degrees Celsius in chlorine gas. Intermediate volatile chlorides form, which are transported, and crystals of zinc tungsten oxide, which is zinc tungstate, are deposited at 980 degrees Celsius. These examples actually describe the importance of the gas phase as a transporting agent and its subsequent influence on reaction rates. Gases react more quickly than solids because mobilities are increased. In reality, the gaseous phase is often important in normal solid state reactions under isothermal conditions where it may act as rapid means of transporting matter from one region of the reaction mixture to another. And this was all about the vapor phase transport in chemical vapor deposition method. This is actually the first method of gas phase methods in which vapor phase transport method is extensively studied, and there we have discussed some of the important examples for the better understanding of vapor phase method. Now let's talk about the chemical vapor deposition CVD. Chemical vapor deposition, which is CVD, is an extremely important way of making high purity thin films and even coatings for industrial applications, especially in electronics and also for fundamental scientific research. It is quite important technique for the making high purity compounds and thin films and even coatings, which is used for the synthesis of electronic components and also important for the fundamental scientific research, just like hydrothermal method. Conceptually, it is simple precursor molecules containing the elements of interest are deposited in the gas phase and products deposited as thin films on every available object in the premises. Early work focused on simple precursor molecules such as volatiles, even unstable hydrides, which include silicon hydrides SiH4 and metal alkyls, which may include aluminium alkydes AlCH3 thrice. For the deposition of elements, only one precursor is necessary. But to deposit compounds, for example, gallium arsenide GaAs, a mixture of precursors is needed. An alternative is to use single source precursors which may contain all the elements of interest and in correct ratio. This necessitates The design of organometallic molecules which decompose cleanly to give the desired product. However, various acronyms are used to describe chemical vapor deposition method, which is actually CVD. Thus, MOCVD refers to metal organic nature of precursors. MOCVD, metal organic nature of precursors. The precursors can be decomposed in various ways by the action of heat or by irradiation. Metal organic frameworks are also very important molecules and capture the renowned interest in recent fields due to their gas sorption properties and even the catalytic properties. These molecules are metal organic frameworks molecules are actually synthesized by using hydrothermal synthesis. The thin films of these kind of materials are actually deposited on the surface by using chemical vapor deposition method. The precursors which are used in chemical vapor deposition method can be decomposed in different ways. For example, it may be decomposed by the action of heat, or it may be decomposed by the action of radiation, irradiation. To prove and to understand these terminologies and the conditions as well, we are better to take some renowned examples. For example, this is silane, actually tetraethyl silicon or silane, SiCH2 and which is reacted with oxygen and change into silicon dioxide and carbon dioxide and water molecule. Gallium hydride in the presence of sunlight or heavy light, it change decomposed and change into gallium metal as well as hydrogen gas. Chromium chloride CrCl2 is reacted with hydrogen at about 600 degrees Celsius, change into chromium metal and HCl gas, while hexacarbonyl tungstate or WCO6 is heated and will get the tungsten element and carbonyl. Diethyl iron FeC, ferrocene, it is actually ferrocene which is reacted with oxygen and changed into iron, carbonyl and water molecules. Gallium GaCH3 thrice and arsenide AsH3 and reacted, heated and changed into gallium arsenide GaAs and methane gas. In many applications such as fabrication of multi-layer semiconductor devices. It is necessary for the films to have the correct structural orientations and be coherent with the underlying layer, in which case uh, vapor phase epitaxy. Vapor phase epitaxy is essential in growth mechanism. These are the some examples which is quite elaborative in terms of CVD. Journal problems which is associated with precursor molecules include: number 1, the pyrophoric nature of alkyls. Pyrophoric nature of alkyls is the first problem which is actually associated with the precursor molecules. The second one is the water sensitivity of alkyls. Water sensitivity of alkyls lead to possible oxygen contamination of thin film products. It means that the alkyl groups actually reacted with oxygen, or it is believed to be the hygroscopic nature behavior of alkyl groups increase the water sensitivity, and which leads to the oxygen contamination of the thin film product. Third one is toxicity of hydrides. Toxicity of hydrides like silicon hydride, SiH4, CH4, and some of the renowned other metal hydrides are quite important and universally accepted. So toxicity of these kind of hydrides is another problem which is actually associated with the precursor molecules. The fourth one is uh, the nucleation of reaction products inside the reaction chamber prior to the deposition as a growing film. This growing film is actually the so-called snowing effect, which occurs because the alkyls with their coordinative unsaturation react readily with electron pair donors such as group 5 and 6 hydrides. These group 5 and 6 hydrides actually uh, because of their coordinative unsaturation react readily with electron pair donors is actually a snowing effect. The fifth one is the need to control accurately the precursors mix with to achieve the desired film stoichiometry and homogeneity. And the sixth one is the variations in volatility and reactivity of the reactants. These are the problems which are actually associated with precursor molecules. These problems are not so insummable that, however, for example, high quality gallium arsenide films have been prepared and used in devices regularly. New single source precursors are being continually developed. The attributes required for the use of MOCVD are that they should be volatile in nature, have stable ligands, pyrolysis of metal ligand bonds clearly, and B of low toxicity. They are also often have other natural advantages such as pre-reaction and snowing are less of problem. The precursors are less reactive towards oxygen and water since they are less coordinately unsaturated than metal alkyls. This is all about this lecture. Thank you very much.